Hi guys, and welcome to Chemistry 1032 Blended class. I am your professor, Dr. Russell Betts, and I will be lecturing you today on Chapter 1 from your textbook. Again, this is a blended class, so don't forget I expect you to watch this entire video, follow along, do the study checks, and make sure you know what you're doing when you come to class, because in class we're going to be doing a lot of practice problems and things of that nature. I will not be actually lecturing in class. I'll be just there to help facilitate your study and also to work with you on problems. So let's get right into the lecture. Now, Chemistry in Our Lives, that's the title of Chapter 1. And I would recommend you download these PowerPoints from D2L, work on them as I work through them. That way you can kind of work along as if you were in a lecture with me. Now I want you to keep in mind I've edited these slides heavily. I'm hitting the high points. I don't want to spend 2 hours on one chapter or 3 hours. I'm just going to hit the high points, the things you need to know. And things I spend a lot of time on, you may want to make sure you remember how to do or know how to do, because obviously I consider those things to be very important. All right, Chapter 1, Chemistry in Our Lives. Chemistry and chemicals, let's start there. Chemistry. Chemistry is the study, composition, structure, properties, and reactions of matter. And chemistry happens all around us every day. That's a very good point, very good statement. Indeed, if you think about some of the things you've done just today, just to get to class, chemistry had to occur. First of all, most of you, if not all of you, came to class in some sort of vehicle. That vehicle had to burn gas. That burning of gas is chemistry. The gas itself is considered part of chemistry because it has a structure and a composition. Things of that nature. Chemistry is basically trying to describe the physical characteristics and reactivity of this thing called matter. Now matter, let me just circle it right here for you, matter is another word for all substances that make up our world. Now we're going to see a better definition of that moving forward in this class. Later on we're going to learn that matter is anything that has a volume and has a mass. But for now, we're just going to leave it as matter is another word for all substances that make up our world. So think about things around you. You are matter. Air that you're breathing is a form of matter. I am matter. The computer you're watching this on is matter. Or the iPhone or whatever you're watching this video on is a form of matter. So matter makes up all things in our world. Chemicals. Now, when you hear the word chemical, I'm sure it brings up negative connotations for most people. Because in our society, you hear stuff like, oh, I won't eat that, that's full of chemicals. Well, it's rather a funny statement, to be honest, because everything is made of chemicals. I'm made of chemicals, you're made of chemicals. How can I say that? Well, chemicals are matter, and we're made of matter, so therefore, everything is made of chemicals. Now, some chemicals indeed are very bad for you, will kill you, in fact. Other chemicals are completely required for life. Now, let's read the definition of the word chemical. A substance that has the same composition and properties wherever found. Well, let's think about a very common chemical that everybody knows. H2O. There's a very common chemical. Water is absolutely critical for life. So, not all chemicals are bad. H2O is a chemical. It's definitely not bad for you. Drinking too much, of course, probably is. Now, no matter where you find H2O, if you look on Mars, you look on Earth, you go to the moon, you go to Europe, wherever, all water is H2O. If it wasn't H2O, it would have a different composition. It would be a different chemical. It would have different properties. Okay? Now, in the photograph, they show toothpaste. Now, I like talking about toothpaste because pretty much everyone's familiar with it. So let's look at the next slide. Now, you don't have to memorize this next slide. I just want to kind of look at it real quick. This is a kind of a list of very common chemicals found in toothpaste. Now, if you look at the top, these are all chemicals, right? If you look over here, calcium carbonate. Now, most people would probably read that and say that's probably okay because it's got calcium in it, and calcium is recognized as a chemical that's probably good for you. Okay? Calcium carbonate is in toothpaste. There you go. Sorbitol. Here's one. Sodium lauryl sulfate. I mean, that has 3 words, right? So that's going to be really bad for you. That's actually a detergent. I wouldn't eat it, but it's a detergent a lot of folks use to clean their hair. I know shampoos have it, some soaps have it, liquid soaps have it. It's very, very common. Titanium dioxide, another common chemical, is actually used to make toothpaste white. It's found commonly in ceiling paint to make ceiling paint brilliant white. Now here's the one I really want to talk about, methyl salicylate. Because if I am sure, I'm positive, if I went to you and I said, here's some methyl salicylate, you should put it on your children's food, you would say, no way, man, you're crazy. This methyl salicylate, that's a chemical, that'll kill me. In fact, if I were to say, hey, here's some wintergreen, throw some wintergreen on your food, I'm sure most of you would probably say, okay. In fact, a lot of our mouthwashes and some of our chewing gum is flavored with wintergreen. You would have no problem with that. But methyl salicylate and wintergreen are the same thing, in fact. So that just kind of goes to show you how in our society, just a chemically sounding name brings negative connotations, where a wintergreen name, but kind of a natural sounding name, makes everyone feel kind of good about that, even though they're the same thing. Kind of just interesting way we think about things. Now here's an example of a everyday kitchen, not my kitchen. Broward doesn't pay me enough to afford these kind of appliances. But as you can see, everything in this kitchen is chemistry. We got the stove, we got the fridge. They're built with chemistry, using chemicals, of course. The fruit, the bowl, everything there contains chemicals, because chemicals are all around you. Some of them are harmful, some of them are completely beneficial. It's just the word chemical just means they have the same structure and composition wherever found. Okay. Study check. Now these are important. Now I think what I would do if I were a student, I would pause the video right now, and then I would try to solve this study check on my own without any help from me. I am going to go over it, but it'd be better if you tried it on your own first. Now in a non-blended class, I would go over this with the class, but I'm not there with you. So let's give you a minute, and you go ahead and you try to figure out which one of the following contain chemicals. I'll give you a hint. Not all of them do. So pause the video now and try. Okay, so you unpaused. Now, which of the following contains chemicals? Let's start at the bottom. Let's start with breakfast cereal. Breakfast cereal indeed contains chemicals. So let's put a little check mark by it. Indeed contains chemicals. How can I be so confident of that? Well, first of all, breakfast cereal for sure has sugar in it. Sugar is for sure a chemical. Breakfast cereal also has likely vitamins added to it. Vitamins are indeed chemicals. Now, what about milk? I'll put a little check mark beside it, because milk for sure contains chemicals. It has water is contained in milk. Lactose, the sugar found in milk. Usually milk has vitamin D added to it. These are all chemicals. Fruit. Obviously fruit contains chemicals. It has water. The juice that runs down your arm when you bite into an apple, that's mostly water with some sugar in it and some apple flavoring. So for sure, fruit contains chemicals. Now, sunlight, I'll put an X beside it, because sunlight does not contain chemicals. Sunlight is energy. Heat and light are forms of energy, and they're not chemicals. They act upon chemicals, no doubt about it, but sunlight itself is not a chemical. Okay? So that's a study check. Now, you may see this study check in class as a quiz. You may not. I'm not saying you will, but you might, because I like to use the study checks as ways to find out if you actually watch the video. Thinking like a scientist, the scientific method. Now, this is a very important topic. The scientific method is the way scientists like to think about problems, because it helps to eliminate emotion from the equation. It also helps to focus your mind into what is really important by following a certain set of guidelines on how to approach a problem. The scientific method relies on this guiding set of principles. First of all, in the scientific method, the first thing you do is you make an observation, which is basically just asking a question about what you're seeing. For example, if your car didn't start, that's a very unfortunate observation, but it happens. First thing you're going to do is probably want to get angry, but you'll quickly realize that even if you get angry, your car still doesn't start. So let's get rid of our anger, and let's take our observations and say, okay, the car won't start. Now what do? Well, we form a hypothesis. Basically, a hypothesis is a very good possibility of what might be occurring with our car. Well, the car won't start. How about the battery's dead? That could very easily be the problem. So if we have a hypothesis, the battery's dead, we must now test our hypothesis using what are called experiments. Now, an experiment for our scenario, a car won't start, could be having your neighbor jump you. Put the jumper cables on the batteries, see if the engine will turn over. Or could just replace the battery with a brand new one. So let's pretend that we go to the auto supply store, we get ourselves a new battery, install it into our car, and it fires right up. So that experiment supports our hypothesis. And then we can draw a conclusion. Well, the car didn't start because the battery was dead. But you have to be careful with conclusions because new experiments can prove your hypothesis wrong, can prove your conclusions wrong. So don't ever marry your conclusion. Just say, okay, all evidence points to this being the case. More than likely your battery was dead. But you don't know that maybe your cables to your battery were loose. Maybe it was just a freak thing where your car didn't start, and we don't know the reason why it just didn't. And if we'd waited 10 minutes, it would have started. Probably not, but maybe. We don't know for sure. But we do know that all evidence supports our hypothesis, so we can draw some sort of conclusion. Let me just go here. Writing numbers in scientific notation. I've skipped a lot of this stuff in Chapter 1. Remember, the slides are posted online. You can feel free to download them and read the slides that I've skipped over. I am hitting the high points, the slides I skip. I'm confident that you can go and look at that on your own without any help from me. Okay? Writing numbers in scientific notation. Now, here's the thing about science. Science often, well, always uses numbers, and often those numbers are extremely big or extremely small. Now, sometimes it's just not convenient to look at numbers that are really big. For example, what if we had a number like this? 3200000000. Oh my goodness, look at all the zeros. After a while, the zeros become really hard to look at because it's really hard to see the forest through the trees. Like, what is that number? Do you even know? I mean, you have to count the zeros. It's very inconvenient. This is called standard notation. Now, standard notation is a valid notation for numbering, but scientific notation would be a better option for this number. Now, let's take a look at what scientific notation is. Scientific notation has two parts. A number written in scientific notation has two parts. Now, here's a scientific number right here. Now, the two parts are the coefficient, the 2.4. That's called the coefficient. Then there's the power. So it's always going to be 10 and a number. Okay? That's called the power. Now, I know this is a little confusing. When we start doing examples, this will become much easier, I promise. And then you put it all together. So it's 2.4 times 10 to the 3. So 2400 equals 2.4 times 10 to the third power. Okay? That and that are exactly the same. They're the same number. One's written in standard, one's written in scientific, but they're the same number. Okay? Now, let's take a look at what all this means. Here we have 2400. And we know if we had 2.4 and we multiplied it by 1,000, we'd get 2400. We get the same number. And we also know if we have this and multiply it by 10 to the 3, we'd get this. Okay? Now, I know that's a little confusing, so let me break it down a little bit more for you. If I have 2400, I can write that in scientific notation like this. 2.4 times 10 to the 3. What that means is 2.4 multiplied. Now, 10 to the exponent 3 literally means multiplied by 10 3 times. So it's 2.4 multiplied by 10. There's 1. Multiplied by 10. There's 2. Multiplied by 10. And there's your third 10. So multiply 2.4 by 10. You'll get 24. Multiply by 10 again, you get 240. Multiply by 10 again, you get 2,400. All right? And that's how this system works. Now, what about this one? The smaller one. Oops, excuse me, sorry. The smaller one. Well, the answer for this one is that. Now let's see how we came up with that. 8.6 times 10. Now the exponent is negative 4. And now you have to remember back to mathematics class. A negative exponent means 1 over. Well, I know that's all mathy. Let's write it down. 8.6 multiplied by, the exponent here is negative. So that means 1 over 10. The negative exponent means 1 over 10. And there's 4 of them, so we're going to multiply it by 1 over 10 4 times. Because the exponent's negative, I know the 10 is in the denominator. So you're going to divide 8.6 by 10, divide it by 10 again, divide it by 10 again, and divide it by 10 again. And that will get you back to 8.66. Now, there should be a way for me to get some drawing tools here. Sorry, bear with me 1 second. Well, anyway. Now, let's take a look at this. Doing the math is all well and good. But let's try to do it in a different way. One that doesn't actually involve math. Now, I'm trying to get some of my editing tools here, and I'm not having any luck. There we go. Let me get some editing tools here to change the color here. And let's erase some of this stuff. There we go. So I want to show you a different way to do this. It's as valid as the mathematical way. It's a little bit cuter though. And it involves a little bunny rabbit. So I want to kind of show that to you. Let's do this now. Let's do it in black. Let's say we wanted to write 2400 in scientific notation. Now I want to talk about a little bunny rabbit. The little bunny rabbit is the decimal point. And the little bunny rabbit likes to hop. And bunny rabbits always want to hop home. And home is always behind the first digit. Okay? So home will always be right there. That's home for the bunny rabbit. So the bunny rabbit, even though he's not drawn, we know it's right here. And he'll hop. 1, 2, 3. So the little bunny has to make 3 hops to the left. So that's a positive hop. To the left is called positive. So that's going to be 2.4. There's our coefficient. All scientific numbers have times 10 to the something. And the something is 1, 2, 3 bunny hops. So put a 3 right there. 2.4 times 10 to the 3. A little easier than thinking about it in the mathematical way. And it's also a little bit cuter, easy to remember. All right. Now let's look at 0.00086. Here's our little bunny. He wants to jump home, and that's behind the first non-zero digit. So home for our little bunny rabbit is right there. Now watch this. Hop, 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 hop. The little bunny had to make 1, 2, 3, 4 little bunny hops to get there. So now 8.6, that's our coefficient, multiplied by 10 to the negative 4. It's negative because the bunny went from left to right, and there's 1, 2, 3, 4 little bunny hops to make the rabbit get there. Okay? So that's how you do it. That's how I do it. I still do the little bunny hop method because I think it's cuter and it's easier to remember, and quite frankly, it's faster. All right? Nothing wrong with the bunny hop method as long as you understand what the math behind it means. Now, here's a study check for you guys. Oop. Sorry about that, guys. I'm still learning the ropes here. There we go. So now, here's a study check for you guys. What I want you to do is convert both of those numbers into scientific notation. What I would do is I would pause the video right now, work out the answers, and then unpause the video, and I'll show you the answers I get. Hopefully they'll be the same. Pause the video now. Okay, you've unpaused the video. So let's take a look. A, 64,000. Well, little bunny's right here, right? 1, 2, 3, 4. Little bunny jumps behind the first digit, number 6. So the answer will be 6.4 times 10 to the 4. That will be the answer for A. Hopefully you all got that. If you didn't get it, pause the video again and try to figure out where you went wrong so that you can correct yourself and get these things right on an exam. B, 0.021. All right, well, the little bunny wants to jump behind the first non-zero digit, right, which is right there. 2.1 times 10 to the negative 2 will be the answer there. 1, 2. Little bunny hops to get behind the 2. 2.1 times 10 to the negative 2 would be the answer to that question, to put it in scientific notation. Okay, so that's how scientific notation works. And that's basically the end of chapter 1. Now make sure you can convert to scientific notation and make sure you can convert back from scientific notation into standard. Now, let me do that real quick. So let's say I have 6.4 times 10 to the 4. And I want to convert out of scientific notation. Well, you just count. Let me get myself some more room here. I didn't leave myself enough room. Let's say we have 6.4 times 10. Let's do a different number. Let's say 5. I chose a different number. So you have 5 little bunny hops you had to do to get there. So 6.4, 1, 2, 3, 4, 5. The little bunny had to jump 5 spaces to the right and put in the zeros. The little bunny hops, the zeros go in between the little bunny hops, right? So the answer would be 64. Okay. Now it's not the same as A because I changed the exponent here, right? So don't get confused. I changed the question slightly. Now let's do this one. Let's go back from that one. So 2.1 times 10 to the negative 2. All right, here's our bunny. Negative 1, negative 2. Decimal point, 0. So it'll be 0.021 would be how you go back from to standard from scientific. It's just a backwards problem, okay? All right, that's the end of chapter 1. Stay tuned for chapter 2.